Dr. Hein. So how I got inspiration for this topic, I was looking at topics to research for this presentation, and I found a quote by Abraham Lincoln where he said, "You never can make a lawyer if you do not understand what demonstrate means." And I left my situation in Springfield, went to my father's house, and stayed there until I could get any proposition in the 6 books that Euclid had said. I then found out what demonstrate means and went back to my law studies. I found this to be very inspiring to study Euclid's elements. And something of particular interest I discovered was in Book 12 of his elements. There's something called the method of exhaustion, which is very similar to what became calculus. So what is the method of exhaustion? The method of exhaustion is essentially a procedure which is based upon the axiom that one quantity can be made smaller than another given quantity by successively having it and doing that continuously. The method exhausts the area of figures by means of successive polygonal approximations, which make the difference in areas smaller and smaller. So like if you're trying to find the area of a circle, as we'll show later on, like you're going to want a shape, and then you'll have a shape inside of it, and then you'll have an additional shapes that you add onto it to get closer and closer to the area of the desired. So some history behind it. The method of exhaustion was invented by Antiphon of Athens back in the 5th century BC. It was really formalized in proofs by Eudoxus. He put it in axiomatic form, and under Eudoxus, it's pretty much how it appears in Euclid, because Euclid just, his books are essentially writing down a lot of things that came before him, for the most part. And we'll talk about that more a little later. Archimedes used the method of exhaustion to find areas and volumes, and he found pi that way. And it was not called the method of exhaustion until the time of the Renaissance. The ancient Greeks did not call it that. And it was also developed independently in China in the 200s AD by Liu Hui. Some history about Euclid. So we know that he was probably educated at Plato's Academy in Athens, and we know that he later trained students in Alexandria, Egypt, hopping across the pond. And so his greatest known work is the Elements, which rendered many previous geometric works of ancient Greece obsolete. The Elements was kind of a compendium of the geometry up to that time. And given that a lot of the documents at that time are written on papyrus, which doesn't last very long, we don't have a lot of the mathematical documents that preceded it, which is ironic enough because we have more documents of the Babylonians and found out because they were written on tile and clay tablets. So the Elements, yes, it relies heavily on the axiomatic method for proofs. This was unique to the Greeks. The Babylonians and the Egyptians developed a lot of early math, but they did not have a formal axiomatic system like that of the Greeks. Theirs was more for like developing plots of land for farmers and geometry. Some of his other works, like the Data, which is an accompaniment to his first 6 books of the Elements, they include problems with magnitudes. There's a few places with magnitudes in the Elements, but for the most part, there is no numbers, like we would call it. Someone else who's of particular importance is Sir Thomas Heath. He specialized in Greek mathematics and classics, and his commentary on the Elements, published in 1908, which is this thick, is of particular importance in the study of Euclid. There was a later edition of Heath that came out, published by Frenchman Bernard Bouchrac. It's published only in French. I only found out about it like a week ago, so I couldn't get my hands on it in time. Your library loan hasn't come in yet. But that's supposed to be the most up-to-date version of Heath and Euclid with modern mathematics. And so we'll get into some of the background of the method of exhaustion. So Book 10, Proposition 1. This proposition is pretty much essential to laying the foundation of how Euclid uses the method of exhaustion in Book 12 of the elements. This proposition is only used in the next proposition after it, and in Book 12. And so, in it, he proves that, he says, suppose there are two unequal magnitudes. From the greater magnitude, over half of the magnitude is subtracted from itself. Then, from what is left over, this is done again and again, continuously. Then there will be leftover in magnitude, which is less than the smaller original magnitude. So he's just proving that, if you cut AB in half, and you keep cutting it in half, eventually it's going to be smaller than CD. So the first place where we see the method of exhaustion in Euclid's elements is in proposition 2 of Book 12. In this proposition, he proves that the ratio of one circle to another is the same as the ratio of squares that are inscribed on those same circles. So, like, imagine these two circles are not the same size, and all four points of the squares are on their circumference. Then the ratio between the two squares is going to be the same as the ratio between the two circles. So that's what he's proving in proposition 2. Here we're not really concerned with all of the proof, we're only concerned with how he uses the method of exhaustion in the proof. And to do this, he starts out with this square on all its 4 points on the sides of a circle. And then by a process of having the distance between these points and then making shapes out of it, he uses the method of exhaustion. So it is halfway between these 2 points, you get a point right here, 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 which is what this looks like. And then with those extra points, you're connecting these lines. And so we started out with a square, now we're adding on a triangle. And as you can see, this triangle is taking up over half of the area that was left over, like right here. And you can do that again. You could bisect these 2 points, and you would get another tiny little triangle right there. And you do that successively, getting closer and closer to the area of the circle. And that's the essence of the method of exhaustion in this example, is exhausting the area in the circle. So proposition 5, this one's a little trickier, but here the method of exhaustion, he uses it with pyramids. In this proposition, he's trying to prove that two pyramids which have the same height will have the same ratio between them as the ratios between their bases. So imagine two triangles, they're not exactly the same. They're going to have the same ratio between them, or they're going to have a ratio between them. And then imagine if you use those triangles as bases for a pyramid, but the heights of the pyramids are exactly the same, then the ratio of those two pyramids are also the same. So that's what he's proving in proposition 5. Again, we're only concerned with the part of this proof, though, that deals with the method of exhaustion. He defines pyramids as prisms with a polygonal base and triangular faces that all meet at a common point. And he defines a prism as a solid figure which is contained by planes, and two of these planes are equal, similar, and parallel, while the rest of the planes are shapes with two sets of parallel sides. So yeah, how the method of exhaustion works, it's very interesting what he does. Very intuitive. So we have a triangular pyramid. This is the base right here. What he does, he divides it up into two equal pyramids, which is one right here, one right here. Those are the same volume. They're exactly the same volume and same shape, and they're also similar to the overall pyramid. And then he also divides it into two equal prisms, which they're not the same shape, but they are of the same volume. And those two prisms take up over half of the volume of this entire pyramid. And in doing this, he's using, prior to this proposition, he proves that you can do this in propositions 3 and 4 of Book 12. He proves that you can do this. And he does this successively on and on. So, like this small pyramid here, what you would do, you put another pyramid here, put another one here, and have two more prisms, which are over half the area of that remaining pyramid. And how the method of exhaustion is used with the pyramids is you would add up all of these prisms in each one, which are over half the area, to approximate the volume of the pyramid. All right, and a few other notes. The proposition 10 is the one we're doing the proof over. propositions 11 and 12 are very similar to proposition 10. All of those deal with finding volumes of cones and cylinders. Proposition 18 is a little different in how it uses the method of exhaustion. It's not at all like the others, really. What he basically just does, imagine this is a sphere, and then we have another sphere we're comparing it to or something, and they have a common center, and then he put like an arbitrary shape in there, and he'd use that for his proof. This one does not involve the continuous resizing that the earlier examples we just went through showed. So now we're to proof of proposition 10. So this is fun. So what we want to prove in proposition 10 is that the cone is 1/3 the volume of a cylinder with the same base and the same height. And to do this, we're going to use two proofs by contradiction. So to begin, we're going to say, let O be the volume of the cylinder, and let V be the volume of the cone. Now let's assume, for our first proof by contradiction, that O is greater than 3 times the volume of V. And so then for the volume of the cylinder, for each different shape that is made at the base, there is a corresponding prism that's the same height as the cylinder. So what he does here, so like the same sort of example as in proposition 2, where we have the circle with the square and all the triangles. It's like now we're trying to compute volume. So we have this rectilinear figure here, and we have these triangular prisms that get added on continuously all around it. That's pretty cool. So, and this gets us a prism P, which leaves over portions of the cylinder less than 0 minus 3V. Another way of wording this, a maybe more understandable way of wording this, is the volume of the cylinder is greater than the volume of the prism we've just made, which is greater than the volume of 3 times the volume of this pyramid. Excuse me. So Euclid then brings in a statement from some previous propositions that have been made, where he's already proved in the elements at this point that the volume of a prism is triple the volume of a pyramid, which has the same base and the same height. So it's kind of similar to what we're trying to prove. And from that we can infer that P, the prism that we made, is triple the volume of the pyramid with the same dimensions, so the same base, same height, and let's call this pyramid K. So we can say that P is equal to 3K, which is less than 3V. And you might ask, why is 3K less than 3V, or why is K less than V? So like if K is, so suppose this is the base of V, the cone, and let's suppose this is the volume, or this is the base of pyramid in it. Well, you can see that the circle takes up a lot more area than the square. So when you're making pyramids and cones, it seems pretty obvious that the cone is going to take up a lot more volume in the pyramid, which proves this. And from this statement, we can then infer that P is less than 3V. However, we've already shown in this proof that P is greater than 3V. So this gives us our first contradiction. So this negates our original statement. So we can now say that the volume of the cylinder O is less than or equal to 3 times the volume of the pyramid B. And again, this is O, this is B. Now, for the second part of the proof, moving on the contradiction, we are going to assume that the volume of the cone B is greater than 1/3 the volume of the cylinder O. And yeah, we're going to use the method of exhaustion in the same way as before, but this time we're going to start doing pyramids. So I'll go back to this image, same base as before, but instead of prisms this time, we have a square pyramid here, and then we have triangular pyramids on all the sides that are getting added on. And triangular pyramids are going to get added on again and again and again until we get to a point. So So all these different pyramids, they will add up, we'll call it uppercase pi, that's notation from E specifically, which has leftover space between itself and the cone less than V minus 1/3. O, which can also be rewritten as the volume of the cone is greater than the volume of uppercase pi, which is greater than 1/3 the volume of the cylinder. Now, again, we know by definition that uppercase pi is 1/3 the volume of a prism with the same base and height. So let's call this prism M. So, and this is, to reiterate, this prism is from the same base and the same height as the cone, or yes, the pyramid that we just made. And from that we can infer that uppercase pi is equal to 1/3 M, which is less than 1/3 O. And then from that we can infer that uppercase pi is less than 1/3 O. However, we've already proved that uppercase pi is greater than 1/3 O. And so those things don't add up, so we have another contradiction. So from those statements, we can negate our original statement, and we know that V must be less than or equal to 1/3 O. So now, putting these two proofs by contradiction together, we've seen that O must be less than or equal to 3V, and we've seen that V is less than or equal to 1/3 O. And you can rewrite this statement as 3V is less than or equal to O. And so putting that statement and the top one together, we can infer that O must be equal to 3V, or rather that the volume of the cylinder must be equal to 3 times the volume of the cone. Now, some important links to calculus. The method of exhaustion was a precursor to calculus. In the 1600s and 1800s, as it was developing, the method of exhaustion was replaced by the things that ended up being calculus. In particular, like Kepler had this really strange idea where he like to find the volume of a circle, and he put triangles inside of it, and he'd do this successively to find the area of a circle. And he'd do the same thing with, imagine this is a sphere then, and this is a cone, and he'd do the same thing with that. And that's a little similar to the method of exhaustion. And someone else that's important to note, Cavalieri, he developed what was called the method of indivisibles. Definitely, a development in calculus where he imagined everything as a bunch of, like if you're finding area, everything's a bunch of parallel lines that are getting added together, or if you're finding volume, it's a bunch of parallel planes that are getting added together. Archimedes actually had really similar thoughts about finding volume and area, and it's very unfortunate that he was killed by that Roman soldier. Another interesting note on the subject, Lewis Carroll, the author of Alice in Wonderland, wrote a book comparing the elements to modern mathematical textbooks of his time, so back in the 1800s. So these are my sources, and thank you.
So we know we're over halfway to the end because you finished the talk and we're ready for questions.
Yes.
Are there any questions?
So why is it more than halfway? Like, why not, like, halfway exactly? Or, like, a third of the way? Like, why was it that ratio?
I think it was half because I'll just go back to a used picture. I think it's half because it doesn't seem like he wasn't really using magnitudes for these examples. But like if I'm looking at this and I'm looking at this, I can clearly see that this is taking up over half of the area that's taken up. I can't say like, oh, I think it's taking up over 70%. My eyes aren't quite that good. But I can approximate 50% better, so I believe that's why.
So, when you talked about Proposition 5, 12, you talk about having a ratio between periods. What does it mean to take a ratio of periods? I'm themselves? Like, what are we taking the ratio of?
I think he's saying like between sizes and dimensions, I believe.
Is there a particular dimension that he's talking about? Because we can change different dimensions.
The height is the same, and it's the base in particular that's different in each case.
Can you go back to that?
Oh,
To
yeah.
that?
Yeah.
So we have the same ratio between the pyramids as between their bases.
Yes.
So we can make the ratio between the bases. But then what is the ratio between the pyramids themselves?
So he's saying it's the same. So like if I guess if these are two different pyramids, and imagine they have different triangular bases, then the ratio between the two different triangular bases is going to be the same. And then if it's a pyramid and they have the exact same height, but again those different triangular bases, they will again have the same ratio between them.
Do you mean like volume, area, length?
The ratio of the area between the two bases would be the same as the ratio of the volume between the two pyramids.
Thank you.
Do we have any other questions? You have a question?
Yeah, would you say that, like, calculus uses infinite methods, right? Like one that's uses infinity. Would you say the method of exhaustion uses infinity, or is it more of a finite then?
I think they talk about resizing continuously in something. I don't think it quite goes to infinity myself. I think it just goes, I think Euclid's just trying to say, we're just going to do this as many times as possible until we prove what we need to prove.
So then the follow-up, could you do all of calculus with the method of exhaustion instead and have it be finite and not have to worry about infinities, which some people don't really like?
It probably wouldn't be as exact.
So I have one more question. Dr. Holstein kind of halfway asked it, so I'm just going to focus on the other half. Can you go back to the principle where if you, I think it was where you divide, if you divide by 2 successively, then the one length is, yeah, there. So this is kind of similar to your question. If you divide by 1/2, I think you're telling us here if you divide by 1/2 enough times, then eventually you'll achieve a length that's less than the shorter length that you're comparing to. And my question is, if that's your axiom, if that's what you assume is true, can you use that axiom to prove that if you cut 1/3 of the length off repeatedly, eventually it would be shorter?
I want to say yes, but I haven't thought about it.
Okay, that's fine. Let's think, Jogan.